of most of the fracture, I mean of the yield first, and later on when we do a example, it'll be 3D. Then we focus on 3D. Okay. So now when we focus on point 4, like what you can see over here, right? You have stress A is equal to minus stress U divided by 2, and stress B is equal to stress positive U divided by 2. Okay. So stress A is negative, stress B is positive. So now when we draw another one, okay, we come over here, right? So we know that stress A is equal to stress U divided by 2. So this is your stress A. Stress B is positive. Okay. So now you can draw a Mohs circle again. Okay. So you can see again, it is inside the blue box. Okay, you can see that for yourself. So that's how Tresca map. Okay, what I'm doing down here is basically from this mapping or from this all this condition, he's able to do a map like this. Okay, he's able to construct an operating map like this. Okay, so I'm showing you the end product and how he got the end product. Okay, and then if we have a P5 condition, so P5, a P5 condition is where stress A is equal to minus stress U over 2, and stress B is equal to stress U. Okay, like over here, you can see P5. So it's minus stress Y over 2 and stress Y for stress B. So now when we construct the Mohs circle, something interesting happened, or something, interesting happened. So we know that stress A is over here. Stress B is over here now. Right? Stress B, come on, Eugene. Stress B. Okay, it's over here. Right, stress B. So now when we construct the circle, what do we see? Okay, so this is bad news, yes or no? The circle is outside the what? The operating regime. Okay, so you have your this region is outside the box. Okay, and when this case material over U, okay, or classically deformed. Okay. So that is why you all remember when I did 2D and 3D Mohs circle, right? I start drawing the what? I start introducing the box to you guys. Okay, why I learned this box from is from all this criteria. Okay, but I want to introduce it to you earlier. So now when I teach this, it's so much more what? Easier for you to comprehend what is going on. Now I got a very interesting question from a student. Okay, a student approached me and said, Eugene, if both points, stress A and stress B, are in this region, okay, let's say stress A and stress B are in, oh, I shouldn't have done that, are in this perimeter, right? In the highlighted perimeter. Will the material fail? Anyone? If let's say your both stress A and stress B are within the circumference and within the box, will your material yield? Anyone? It will yield. Any idea why? This is because you cannot isolate the certain part of the circle that is not going through that stress field. Let me elaborate, okay? So for example, this is our, stress A. Sorry, this is our stress A. And this is our stress B. Okay, this is our stress B, for example. Okay. So this is our center of the circle. Okay. If we rotate our element, okay, so if we rotate our element, okay, from point A, we rotate our element by this much. Okay. So I'm going to measure, right? We are going to rotate our element from point A. We are going to rotate clockwise by 60 degrees, approximately. Yeah, 60 degrees. And from point B is also going to go 60 degrees. So I'm going to call this stress 60 or stress A60. And this is my stress B60. Okay. So the material is still under the same stress state. Okay, so this is the stress state it's in, or the applied load. When we rotate this by 60 degrees, so this is the original. This is the original. Okay, so this is the original. So we rotate 60 degrees, right? We rotate 60 degrees anti-clockwise. 60 degrees anti-clockwise. I'm trying to draw this with my protractor. Okay. Okay. So this is 60 degrees. Oh no, 30. Eugene, come on. You're teaching Mohs circle. On element is on Mohs circle is 60. On element is 30. Eugene, come on. It's a long week for me. 30 degrees. Okay. Lucas will say something, I know, if I've done that wrong, Lucas. Right? So when we rotate that, and when we rotate that, right? And when the element is at this stage now, right? Anti-clockwise. So what we will see now is the element is still going to see compression. Okay, the other side is tension, right? And the shear is going to get is this shear direction. Okay, this value will be at what? Stress A 60, stress B 60, and shear 60. Okay, so this is our, at this intersection, this is our shear 60. It will be outside the what? It will be outside the operating boundary. Can you see that? So the material will yield. No doubt, this is the applied load. The applied load did not change. I repeat again, the applied load is still constant. So the applied load are still within the what? Within the box, right? But when you rotate the element at a certain angle, for this case, 60 degrees on most circle, 30 degrees on the element, right? You will see a stress state that is outside the what? Outside the operating regime. Okay. So your material will what? Will yield. Okay. And maybe the student that asked me this question is around. He asked this very good question. Okay. He told me, Eugene, if we are in the yellow highlighted region down here, means the material will not yield. And then when I think of it, yeah, no, it will yield. You understand, right? Because the circle is still the circle is still the same size, but part of it is outside the shaded region. So what I'm trying to tell you is this, okay? When you want to get married, you don't just marry the man or the woman. You marry the whole family. Are we clear? Okay, you don't get to pick what you like and what you don't like. Okay. Moral of my story. Okay. Now let's now look at a very interesting problem. Okay, this problem is a good problem. Okay, and this problem, we did this problem in the first day of class. Okay, now when I start doing this problem, you say this is peanuts, man, monkey food, you know. Okay. Now when you read this statement, okay, you absolutely understand what it means now. Okay, so this is example, and this is a long example. If in a few years time you go to industry and you're going to design and analyze stresses in a product that you'll be making, you forget, go to this piece of paper over here. Okay, this spells it all. Okay. So if you look at this problem, it's exactly the same problem we did in week 1. There you go. Okay, this is week 1. Okay. So now we are going to go through everything that is described down here. And now, if you look at week 1, you will understand what is going on now. Okay. And we are going to go through this procedure. Okay, you see this procedure that I've written down here. We are going to go through the whole thing, but now you actually know, yeah, now we understand, we comprehend what we are trying to go through, okay? So we have an internal load at a critical section. So when they say, okay, let me read first, okay? On a steel shaft of a ship, I calculate to have a torque of 2,300 pound-feet, a bending moment of 1,500 pound-feet, and an axial thrust of what? 2,500 pounds. Okay. If the yield for tension and shear are 100 ksi in tension, and the yield is 50 ksi, respectively, determine the required diameter of the shaft using the maximum shear stress theory. Okay. Now, in an engineering problem, okay, you decide what criteria you want to use. You will not use the maximum shear stress criteria. You decide. Are we clear? Okay, this is just a working example. It bounces within a certain boundary. Okay. Right. So now you see the shaft down here. Now, question for you. Can we use the equation that we have done with transmission shaft? I repeat again. Can you remember this formula? I think the formula is I can't remember the formula. I think it's C over J is equal to square root of Tx squared plus by My squared plus by Mz squared divided by shear stress allowable. Right? So this is for what? This is for transmission shaft. So I'm asking asked, can we use the transmission shaft? Yes, why, no, why? Anyone? I see you shaking your head. Why? Well done, okay? We cannot use this because this cannot be applied because there is what? There is an axle applied. That is what engineers from McMaster should know. When to apply what, when not to apply what. Okay, that is very, very critical. Okay, so you can see over here we have a 2,500 pound-feet or pounds of axle load, and that just like oops. Okay, now, so before we start on the problem, so we know what we know is this face over here, right? This face over here, I'm shading in red. Okay, it is the phase where failure will occur. Okay, it is the phase where failure will occur. Okay,